All right, so in the last video, we finished by talking about how the arc length function can apply to functions where x is given as a function of y, and now we have a function like that. So we want to find the length of this guy, x equals y to the 4th over 8 plus 1 over y, 4y squared. Okay, so I'm going to just write that slightly differently because I kind of prefer things written this way when we have to take derivatives. This is plus 1/4 y to the negative 2nd power there. Okay, so using that that formula on the previous page, we know that it's dx dy that we need. So I have to take a derivative of this before I can go any further. This is going to give me 1/2 y cubed, and this will give me negative 1/2 y to the negative 3rd power there. Okay, so that's just the derivative. Now what I need is 1 plus that derivative squared, because in my arc length formula, that's the thing I'm taking a square root of. So let's find that next. 1 plus dx dy squared. Okay, now the dx dy, whoops, if I square that, this is going to look like 1 plus 1/2 y cubed minus 1/2 y to the negative 3rd power squared. Okay, and so if I square that out, I'm going to actually give myself a little bit of space because I'm going to use that 1 and I'm going to write it differently in a second. But if I were to square that out, what I would get is 1/4. Actually, sorry, I'm not going to do that quite yet. I'm going to have my 1 here. 1 plus 1/4 y to the 6th. When I multiply these two things together, y cubed times y to the negative 3rd power, those are reciprocals of each other. So I just get a 1, but then I have a 1/2 times a 1/2 there. So that's going to be 1/4, or technically negative 1/4 because of the minus there. But then I'll get another one of those terms and just end up with a negative 1/2. Finally, plus 1/4 y to the negative 6th power. Here I can combine these two, so 1 plus negative 1/2 is going to equal, well, let's get these in a slightly different order. That's going to be plus 1/2 there, plus 1/4 y to the negative 6th power. Now here's where something I'm keeping in the back of my mind this whole time. This is going to be something I need to take a square root of eventually. So right now, when I see the form of this thing, it's not obvious to me what the square root of this is going to look like. But if I'm somehow able to get this thing to be written as a perfect square of some kind, then I know that the square root is going to cancel that perfect square out. So that's kind of my goal. I'm going to see if I can write this as something squared, which means I want to try factoring this down. What I'm going to do is I'm going to factor 1/4 y to the negative 6th out. And I'm doing that because negative 6 is the smallest exponent that I see. If I do that, this 1/4 is gone. This is going to become y to the 12th. And you can verify, because if I distribute this back in, you should get this 1/4 y to the 6th term there. Here, if I factor a 1/4 to the negative 6th power out, I'm going to get plus 2y to the 6th power there. Again, distribute that in, verify that 1/2 is what you end up with. And then this guy, I factored that entire term out, so it's just plus 1. Okay, I'm going to go off to the right here. This is the same thing as 1/4 y to the negative 6th times y to the 6th plus 1 squared. So that thing in parentheses is a perfect square trinomial, which is great. That's kind of what we wanted to see. So now we can deal with the square root. If I want the square root of this, I'll include that in there. I'm going to put these square roots over all of these previous steps that I just did. Everything in here is easy to take the square root of. I end up with 1/2 y to the negative 3rd power times y to the 6th plus 1. Okay. And at this point, I'm going to distribute this back in. So this would look like 1/2 y to the third plus 1/2 y to the negative third. Okay. Now I'm pretty much ready to integrate. So my arc length, this is what my integrand is going to look like. I did all of this work to simplify it down to this. I see a common factor of 1/2, which I know can get pulled out of that integral. 1/2. As a reminder, the interval that we're integrating over is 1 to 2. So those are my limits here. Okay, integral from 1 to 2. And then after factoring that 1/2 out, I'm left with y cubed plus y to the negative third dy. Just want to take a second to remind you, when you have more than one term in your integrand like this, make sure you're putting parentheses around it. The common mistake I see is people forgetting those parentheses, and that's technically a notational problem. So you want to include parentheses when you have more than one term here. Okay, this is a really easy integral to do now that we've simplified it as much as we have. So we're going to get 1/4 y to the fourth, then minus 1/2 y to the negative second power. And again, we're going from 1 to 2 there. Okay. This is really straightforward evaluating this. So I'm going to do this, dot, dot, dot. You can do the arithmetic and fill in those gaps. I'm going to jump to an answer. You're going to end up with 33/16 in the end. Okay. It's good practice for you. You do that work in between here, but we're going to skip it on this video. All right, so that's example number 2. Now let's kind of finish this section out with something called the arc length function. So coming back to our formula on this page, here's what we've been using in the last 2 examples, or at least versions of this. Definite integral from a to b of this square root here. And this specifically gives me the length of an arc on the interval AB. So again, here's the original picture that we used. It's the length of the arc that goes from A to B. Now sometimes for a specific curve, y equals f of x or x equals g of y, depending on the form that we're putting it in, we may want to use the same curve to find several different arc lengths in the same problem. Specifically, there's examples where we want to keep the same starting point, but look at lengths of different arcs. So that would basically mean that we're using different values of b to determine different end points, and then compute all of these arc lengths. It's cumbersome to have to go through all of these steps every single time we want to do that for the same function. So what's better is if we have a function that we can get from this one that just spits out arc lengths for whatever endpoint we plug into it, whatever value we choose to use as our b. So what we're going to do is we're going to take this arc length formula, and the b here, which represents that right endpoint for that interval that we're integrating over, we're going to change that from a constant to a variable. We're going to change that b to an x, and then just let that x kind of vary so that we can plug different things into it and get different arc lengths. Okay, so that's where this formula right here is coming from. S is the symbol that we use for arc length. So s of x, notice it's a function of this x right here. It's a function of that upper limit of integration. So we're going to change this from a to b to being a to x. And then I still have the same, radical in my integrand here because it's still the arc length that we're talking about. But all of the x's that used to be there, I have to change to t's. And that's because I'm already using an x here. I don't want to confuse it with a different x over here. We call that t a dummy variable because it's basically just holding the place of that variable. But after we do the integration, it's going to turn into something else in terms of x. So the t is kind of a temporary holding place for that variable. Okay, so this will give me the length of an arc of that curve, f of x, going from a to x, or f of t going from a to x. Okay, now before we do an example with this, there's a little bit of work we can do with this definition to get some useful stuff. So if I were to take this definition of my arc length function and differentiate it with respect to x, so if I wanted to find s prime of x or ds dx, depending on how we write that, this looks like the first part of the fundamental theorem of calculus, which in Calculus 1, you may remember, deals with integrals where that upper limit of integration is that x. When you take the derivative of this, then that derivative, in a certain sense, cancels that integral, and you get the integrand as your result, but the t is going to change to that x. So if I were to differentiate this, I would get ds dx equals the square root of 1 plus f prime of x all squared, or in Leibniz notation, 1 plus dy dx squared. Okay, so this is what the derivative of my arc length function looks like. Now, from this, if you remember talking about differentials back in Calculus 1, we can define the differential ds as this expression times dx. So a way of remembering that is if we interpret that ds dx as if it were a fraction, and then multiply both sides of this by dx, you end up with this thing right here. We call this the differential of arc length. Okay. Now, we could do even more with this. So if I were to think of, again, this thing as a fraction, the dy dx, then I could write that as 1 plus dy squared over dx squared. Okay. And then I also have this other dx right here. If I were to factor a 1 over dx squared out, so something like this, this would become dx squared plus dy squared times dx over the square root of dx squared. So I'm taking this dx squared and this, oops, I just realized I was off the screen there. I'm taking this dx squared in the denominator and basically factoring it out. It's taking that radical with it. But then if I were to take the square root of that, that square root of dx squared just becomes dx, which cancels with this, and I'm left with just the square root of dx squared plus dy squared. Okay, remember this whole thing is ds. That's what we're defining ds to be down here. So if I square both sides of this, I can get this little expression, ds squared equals dx squared plus dy squared. Now this is where these ds, dx, and dy terms are differentials, for the way that we define them all the way back in Calculus 1, and they represent something specific. So it may have been a while since you talked about this. As sort of a reminder, the dx represents the same thing that a delta x would represent. It's the change in x as I go from this point to this point here. Okay, so that dx represents that change in x. Delta y would represent the corresponding change in y. So notice it's depending on that change in x, but it's the corresponding change in y in our actual function. Whereas dy is an approximation to delta y, and it represents the change in y, but along this tangent line at this point right here. So if this is the value of x that kind of represents the starting point for our x values, we can find a tangent line there, and the change in our tangent line in the y direction is how we define dy. So you can see in this case, this dy is actually bigger than delta y, but in general, it's an approximation to that delta y. Delta s is a similar concept. So remember, s represents arc length. Delta s would represent the actual length of this arc over this interval that we're using the dx to determine. So it's as dx, or as x changes from this value to this value, our arc makes this little shape from here to here. Delta s represents the actual length of that arc, whereas ds is an approximation to it, and that ds is dependent on this dx. Okay, it's technically dependent on dx and dy, but since dy is also dependent on dx, then we can just say it all depends on what dx is. But you can see from the relationship here that ds, if this is true, if this is the relationship between ds, dx, and dy, then this looks like the Pythagorean theorem. So we can interpret ds as the hypotenuse of this right triangle, which is just a piece of that tangent line right there that we're using as an approximation to the actual length of that arc right there. So that's geometrically what that ds represents. It's an approximation to that change in our arc length from here to here. Okay? This is a concept that gets used more in Calculus 3, but it's useful to introduce it here. So we have one example left to do. We want to find the arc length function for this curve, inverse sine of x plus the square root of 1 minus x squared, starting at the point 0, 1. So anytime you're being asked to find the arc length function for a given function, you have to be given a starting point. Because, again, if we go back to that definition, there has to be some lower limit of integration that we know, because we're going to put that here, then we can evaluate s of x. So this is my function. This is my starting point, 0 to 1. So 0 is the x value. That's going to be the lower limit of integration. We're not at the step where we want to do the integral yet, though. We want to set up our integrand. So we know that the first thing we need is y prime. Okay, so I'm going to take the derivative of the inverse sine, which is 1 over the square root of 1 minus x squared. And then the derivative of this guy is going to require the chain rule. You can work out the details, but this is one that you should have seen probably in Calculus 1. It becomes minus x over 1 minus x squared. Okay, this is just using the chain rule to get here. Now, it's convenient that they have the same denominator, because that means I can take this and put it all into one fraction. But before I do that, I know that, well, actually, no, let's do that here. 1 minus x over the square root of 1 minus x squared. Okay, we know that our integrand is going to involve a 1 plus y prime squared. So this is going to look like 1 plus this thing squared, 1 minus x, all over the square root of 1 minus x squared. And I'm going to square that, okay? My goal here, again, is eventually to take a square root of this entire expression. And because this expression involves two terms, it's not really ready to be dealt with as far as the square root is concerned. So we kind of want to simplify things down to a point where finding a square root of this expression is easier. What I'm going to do, if I square this guy, I'm going to get 1 minus x quantity squared, which is 1 minus 2x plus x squared. That's what I get if I square that numerator, over my denominator squared, which is just 1 minus x squared. Okay, I'm adding a 1 to that, and I would prefer if I had just one big expression instead of two separate terms here. So I'm going to write that 1 as a quotient with a common denominator, 1 minus x squared over 1 minus x squared. So my 1 has changed into this. Now that I have that common denominator, I can add these two things together. I'm going to end up with 2 minus 2x. And then my negative x squared and my positive x squared there are going to cancel. Okay, I also noticed that my, well, actually, let's do this in the next step. I have 1 minus x squared. I can simplify this even more. So if I were to factor a 2 out of my numerator, I'll have 2 minus 1 over x. And then my denominator, I'm seeing a difference of squares. So I can write that as 1 plus x, 1 minus x. I get cancellation happening there. So this whole thing becomes 2 over 1 plus x, which is way, way simpler than what we started with. Okay, now at this point, I want to remember that we're technically taking square roots of all of this stuff. So I've kind of waited until this point to write all of these square roots in. Okay. If I take the square root of this guy, I can write that as root 2 times 1 plus x to the negative 1/2 power. That's the same thing as what the square root of this would look like, but I'm using a rational exponent instead. Now we're at the point where we can look at our arc length formula. So my arc length formula, s of x, is equal to the integral from a to x, but remember a is 0 for this problem. of this integrand, but this is where we want to change any x's into t's. So this is going to look like the square root of 2 times 1 plus t to the negative 1/2 power, and this would also be a dt right there. We're just going to evaluate this directly. So the square root, or the integral of this is going to look like 2 root 2, 1 plus t to the positive 1/2 power. And we're going from 0 to x here. So if I plug in an x, I'm going to get 2 root 2 times 1 plus x to the 1/2 power. Which is the same thing as the square root of 1 plus x, so we can write it that way. And then when I plug a 0 in, I get 1 plus 0 to the 1/2 power, which is just 1 times 2 root 2. So both of those terms would have had a 2 root 2, which I'm going to choose to just factor out like that. But that would leave me with plus, or minus 1 in there. Okay, so this right here is my arc length function. Now, that's part of the question. That's part of what it was that we were trying to find. So I have one more part to this question. Use this result to find the length of the arc of this curve from 0, 1, our starting point, to 1 pi over 2. So the benefit of having this arc length function is I've done all the integration I need to do. All I need to do now is plug in whatever value of x would answer this question. So remember, x came from this upper limit of integration, which represents the x coordinate of our ending point, or our terminal point for this arc. It's the 1. That's what I'm plugging in. S of 1. Okay? So if I were to plug in a 1 here, I'm going to get 2 root 2 times, okay, so here 1 plus 1 is 2, so I get the square root of 2 right there, minus 1. You can see where the x got plugged in. At this point, I can just kind of distribute things in. So if I distribute that root 2 in, I'm going to get 2 root 2 times root 2, which is 4 minus 2 root 2 as a final answer. Okay? If I then were to ask like a follow-up question and say, okay, now in addition to that, let's find the arc, or the arc length of the curve that still starts at 0.1 but maybe goes to a different point. All I would have to do is take the x coordinate of that new point, plug it into this function, and I would only have this much work to do. So that's kind of the benefit of finding these functions. We can repeat this process for the same curve multiple times with very little work to do. All right, that's going to wrap up 8.1.